algebra from the problems of chapter 9. Those could be good problems. Now, this equation that you just mentioned, this is the second derivative of x with respect to time plus omega squared x. This is equal to 0. Now, you are electronics engineering. You are going to see these differential equations in the second year and in the third year a lot. Okay. Now, in here, one thing I have. Let me say it this way. The most important thing for an engineer is the first one is to check the units. Okay, so let me write it this way. Okay, so first thing, check units. Okay, second thing, check order of magnitude. Okay, so a student who comes to an exam, order of magnitude, and does the units wrong, they get 0 points, okay? The second part is check the order of magnitude of some quantities. You may not have a calculator, but you should be able to check 10 to the power 2 divided by 10 to the power 4, you get 10 to the power minus 2. So this is the order of magnitude. The third part is give precise results, okay? This is the last one. Give precise...
Professor, once again, what was the order of magnitude?
Oh, the order of magnitude is that, for example, you are in an exam and you have to calculate what is the k. Okay? K is equal to omega over lambda, and omega is 2 pi times the frequency. Lambda, it is 3 centimeters, and you need to find k. In this case, what do? You say 2 times pi times the frequency, which is 3 gigahertz, 3 times 10 to the power 9, okay, divided by 3, sorry, this is 3. What is a centimeter? Centimeter is 10 to the power minus 2, okay? So this is gigahertz, hertz, this is meters, and then what do? You divide 3 by 3, 10 to the, this is 2 pi, okay, times, what is this? 10 to the power 11. This is the order of magnitude. 2 pi, it is 6, so this is approximately 10 to the power 12. This is the order of the magnitude, okay? Maybe you don't have a calculator to write exactly the numbers, but you should be able to check quantities like this, okay? This is the order of magnitude. Now, let's check the unit. What is the unit of this equation? What is the unit of x?
Meters.
Meters, that's correct. So let's write here, we have meters. What is the unit of d over dt? What is this? What is the unit
power of 1 minus 1.
It is 1 over second. That's true. This is 1 over second, okay? So, what is the dx over dt? What is the unit of this?
Meters per second.
That's true. This is velocity, right? This is equal to meter per second. Then, what is d squared x over dt squared? What is the unit of this?
Meters per second square.
Yes, this is acceleration, so it is meter per second square. That is true. So then, what is the unit of this? So this is, what is the unit of this whole term, the first term? This is what it is, okay? Plus meters. So what is the unit of omega squared?
1 over second square.
That's true. The unit should be the same, right? The unit here plus the same units, we should get 0. 1 over second squared. This is equal to 0. That's good. We're just checking the units. What is the unit of omega? What do you think?
One over second.
That is true. This is 1 over second. 1 over second is in fact equal to hertz. Hertz is the number of cycles that occur in 1 second, or in 1 unit of time. Now, this is 1 over second, it's an omega, but we can write also this one as radian per second. So this is like an angular velocity, radian per second. And radian is not a unit, so you sometimes you don't even see it, but that's what it is, okay? So it looks like we have an equation, and this equation is an oscillatory equation, okay? So you can try, let's check if x, sorry, this is not good. Let's check if x is equal to e to the power I omega t. Okay, let's assume x is this. Then what is the first derivative of x? What is d over dt? What is the derivative of e to the power ax? What is the derivative of this term?
A times e to the power of ax.
That's true. Okay, so this is the general rule. So if this is x, what is the derivative of x with respect to time? What is a in this case?
I omega.
That's true. This is I omega times e to the power I omega t. Then what is the second derivative here? This is I omega again. So it is I omega all squared e to the power I omega t. I omega squared is equal to minus omega squared. Because I squared is minus 1. This is minus omega squared e omega t. Okay? So then, if this is true, what is, so let's find here, what is omega squared x? Omega squared x is equal to omega squared e to the power I omega t. Okay, so now what you need to do is, because we have to check whether this is true, right? So then you have to add this term plus this term. What do you get if you add these two terms?
Professor, one question. How do we come up with x equals to e to the power of I omega t?
I'm giving it, okay?
Okay.
We provide it. So what do you get if you add this term and this term?
0.
0, that's true. So it looks like we check whether this is a solution of this differential equation. Apparently it is, okay? So these equations, they have the solutions are always oscillatory, and you can try this at home by checking whether x equal to cosine omega t or x equal to sine omega t. Check whether these two expressions are roots of this differential equation. But in this class, we are not discussing the solutions of this type of differential equations. We are just considering linear differential equations. And now you don't need to know in detail what is the nonlinear differential equation, but think for a moment that we have to deal with derivative of y with respect to time. This is equal to ky. Okay? This is what we are going after. And to solve this one, the solution of this differential equation, it is the following. Y is equal to y0 e to the power kt. Okay? We can derive this one. How do we do it? We can divide, we can write it like this, dy over y. This is k dt. We integrate both sides, and here we get natural logarithm of y is equal to a constant times, kt. Then we put the exponential, this is a constant e to the power kt. Okay, so this part is a proof of this. You can take this for granted. We have shown this one in the previous classes. So we are talking about this type of differential equations. So it looks like we have the rate of change of one of the variables. It is a function of the variable itself. This can get a little, we can have also another differential equation. This can be the following: dz over dt is equal to alpha z, then z would be equal to z0 e to the power alpha t. Okay? So these two are two differential equations. Now, this can be a little more challenging because we could have a system that looks like this. We could have dy over dt. This can be equal to k1y plus k2z. So the y, it does not depend only on the y, but it depends also on the other variable. And here, dz over dt, this can be equal to k3y plus k for z. So here we have a system of differential equations which are coupled. Okay. What does coupled mean? Being coupled means that y is affected on z, so it changes z, and meanwhile z is immediately also affected on, depends also on y. So, and whenever we see a system like this, we immediately think about the properties that linear algebra can help us to solve different difficult problems. And now here we have a system which is coupled. We want to have a decoupled system. What does decoupled mean? Decoupled means that we can rewrite this, we can find a new basis which will depend on K1, K2, K3, K4, and then we can solve the problem in that domain. Okay? So in this case, we can say that y dot, so with dot we denote derivative with respect to time. Okay? This is z dot, so here we have a vector, and these are the values of K1, K2, K3, K4, and here we have y and z. Okay. Meanwhile, did you find any problem regarding the differential equations that we can solve from the book?
Yes, Professor. You have one in page 299, an example.
Example. Why don't we look at a problem? Because examples, they have the solutions on the book. What do you think about this?
Okay, that would be good as well. Let me see if I can find anything.
Mr. Professor, general exercise would be really nice if we solved it.
Then on what topic?
On differential equations, an example that
Yes.
we need it in the test, you know.
Sure. Yeah, but that's why I'm saying, find for me a problem from the book which is dealing on differential equations.
Professor, problem 9.7.
You know, this 9.7, I solved this one with software engineering. You can watch this one. It is recorded, the solution of this one, okay?
Okay.
9.8, we solved also this one. Let's see if we can find. Okay, so it looks like we've solved. Do we have any other system?
Professor, with this problem with software engineering, can you solve it again? Because it's different when you solve with us and different when you see the recording, maybe.
Of course. So we only solved the 9.7, right?
Okay.
Which one did you choose? 9.7 or 9.8? Сидите с уровнем сделать?
The one you did with software engineering, I guess.
Okay. 9. Okay, then let it be 9.7. Okay.
Professor, so we need to transform this matrix of k's, k1, k2, k3, k4, to a diagonal matrix, right?
That is true. So what we always do is the following. We have, this is the matrix A. So once we have the A, we should very fast obtain D, P, P inverse, okay? This is it. Okay? So let's look at this problem that we have in the book, which is the following. We have here an example. We are given a system which is y1, y2. So we have the first derivative of y1 and the first derivative of y2. They are equal to, you know, you have the problem over there. Allow me to write this one immediately like in a matrix form. So this is equal to, what are these coefficients? 1, 4, 3, 2. 1, 4, 3, 2. And we multiply this with y1, y2. Okay, so this is our equation. The initial conditions are 1 and 0. Okay, so we are given that y1 0, y2 0 is equal to 1, 0. Okay, and now the question is, we need to find y1 as a function of t and we need to find y2 as a function of t. This is what we need to figure out. And let's keep these numbers here for a while, or let's do it like this. Wait a second. Okay. So let's first give the standard basis. This is the standard basis, and here we are dealing with y1 and y2. Okay. And then this is the other basis, and this other basis, let's assume that we have a pair of variables, u and v, over which we can solve the system. Now, we know that we should be able to determine a matrix P, which can bring us to the standard basis. Right? We have also the initial condition 1, 0, which is right here. We start here with 1, 0. And the question is the following. We have x0. It's a vector. And we need to find xt. Okay? This x0 and xt is composed of two variables, which are shown here. Now, what is the general solution in this case? The general solution is the following. We say xt is equal to at times x0. Okay? So this is how the solution can be found. So let's draw this one in red color. So from here, we can follow this path. Okay? That's what we can do. But now, but this is difficult because it's a differential equation and it is really tricky. Okay? It's not that it takes a lot of time. It's not only that. It's that also we don't know how to generate these. So for this one, what we do is that we don't follow this path. What we do is that we bring this problem, we bring this in the new basis, and we define a vector u0. So this initial condition, where y1 initially is equal to 0 and y2 is 0, we want to reinterpret this whole problem and we project it here. After we project here, we find the ut, which is how it generates in time, and from this ut, we come this way. But how we find ut, we find it this way. We have to rewrite this system. And by the way, wait a second. So this is derivative of ut. Here we have the derivative of u. This is equal to d times u. Let's write it like this. This is enough. Okay. So what we see from here is that we have y1, y2, up. Okay, we have the matrix A here. Here we have to consider the matrix D. So now let's assume we are in an exam and we need to solve this relatively fast. So how do we do it? Initially, we have to figure out what are these initial conditions in the new basis. Okay. And let's also note this one. So you see this differential equation? This one is this, okay? And now we want to solve for this system. We have A, and for A, the first thing, we need to calculate the eigenvalues, lambda 1, lambda 2. Okay, so we need two equations. Let's first look. What is lambda 1 times lambda 2? What is it? It is equal to the determinant of this matrix, okay? So there is a property, we can say that this is equal to the determinant of A. What is the determinant of A? It's 2 minus 12, it's minus 10, okay? And then, what is lambda 1 plus lambda 2? This is equal to the trace of A. What is the trace of A? Is equal to 3. Trace of A is the sum of diagonal terms. And then, so we have two numbers, two equations. So if it is a 2 by 2 matrix, we can even find the numbers like this. So immediately, it looks like lambda 1 is equal to minus 2, and lambda 2 is equal to 5. Okay? So this is a good combination. So in 1 minute, we figured out what are the eigenvalues, 2 minus 2, 5. So that's good. So we know this, and we say that the matrix A is going to be 1, 4, 1, 2, 3, 4. So let's do it like this: 1, 2, 3, 4. But this matrix in the new basis is going to look like -2, 0, 0, 5. Okay, we found this. So, did we spend much effort here? No. Now that we have this matrix, then we say the following. We say the derivative of u, or we can even put another variable. We can sort of say the derivative of v, and the derivative of w, this is a vector, this is equal to a matrix which is -2, 0, 0, 5, times vw. Okay, these are just variables. What is the first equation? So let's have a look at this. This one here is equivalent to this. Which one is more simple? So this system here, this is coupled. So it's intermixed. This one is decoupled. And that's what we wanted to do. If this is decoupled, what is the first equation? Who can read this for me from the class? Someone?
It's -2v, and w is for the w.
Yes. Is this a difficult system to solve or not? This is simpler because let's have a look of how does this other system look like. The other system, it looked like this. Y1 dot was equal to y1 plus 4y2, and y2 dot is equal to 3y1 plus 2y2. So you can have a look again how this one compares to this. This is much simpler because here we can immediately say that v is equal to v0 e to the power -2t, and w is equal to w0 times e to the power 5t. Okay, we solved this one. That's it. We solved this problem, and what should we do next? We should find a matrix P. Okay, we should find a matrix P so that we can transform this solution back to this other side. But so we found matrix D right away. Okay, because it was composed of -2 and 5. That's why we need.
Can I ask something?
Yes, sure.
How do we, like, why do we write this v equals to v0 times e to the power of -2t and the other one?
Because
Is there a rule?
we need to solve this the differential equation.
So it's a rule.
Yes, it's a rule because we saw it here. Can you check this?
Yes, so that's the general case. Okay.
Yes, or if you don't want to consider it like a rule, you can write it like this. This is dv over dt. This is equal to -2v. You divide both sides of the equations by v. Okay. You can multiply both sides of the equation by dt. That's fine. So you cancel the dt here. You cancel the v. What is left is dv over v. This is equal to -2 dt. Okay. You integrate both sides of the equation, and you get ln of v, it's equal to -2t, okay? And then you take the exponential, this becomes v is equal to v0 e to the power -2t. Okay, you can always recalculate this one, okay? Are we fine?
Yes, now it's
Professor,
clear.
Yes.
what is age there?
What is a?
Age, yeah.
H, I don't see an H. It was ln, natural logarithm.
Oh, okay, I got it.
So 1 over x dx, the integral, it's a natural logarithm of x. Okay, this was something from the...
Professor, sorry to interrupt again. What is trace? How do we find trace?
Well, trace is the sum of the diagonal terms in a matrix. Trace is 3, is this.
Ah, okay.
Okay. Even if you have a 3 by 3 matrix, the eigenvalues will always be equal to the trace. So, so now we should find the p. If lambda is equal to
Professor,
-4,
I have one question.
yes.
There, when you've written dy over dt equals k times y, that k is in fact the eigenvalue, right?
No, it's not. K is just a constant k. Oh, in this case, sorry. In this case, it corresponds to b the eigenvalue. That's true. Yes. But this is the general solution. If this is a constant times y, this is the solution. Okay. But in this case, it's true. It's an eigenvalue. Are we good?
Professor,
Yes.
Why did you go for lambda 1 minus 2 and lambda 2 5? Because there are many combinations. Why
No,
that?
there are many, only two. It's impossible to be many. Because
For
you should
example,
have
1 and 2.
the product of two numbers equal to minus 10. These two satisfy, and the summation of these two being 3, they are also
Okay, yes, okay.
And now you can also do it like this. We got these two relationships. Then you can do the following. From this equation, lambda 1 plus lambda 2 is equal to 3. You can write that lambda 2. Lambda 2 is equal to 3 minus lambda 1. Okay? 3 minus lambda 1. And then you can say lambda 1 times 3 minus lambda 1. This is equal to minus 10. So you can come up with a second order polynomial, which is minus lambda 1 squared plus 3 lambda 1 plus 10. This is 0. And here you can use the formula of minus b plus minus b squared minus 4ac, right? Okay? And if you try to solve this one, you're going to find the same solutions. Okay? Are we good?
Yes.
Okay, so now we need to find the matrix P. What is matrix P? For lambda equal to minus 2, so we always write this, right? A minus lambda I. Then we get the following. 1 minus 2. This is 1 minus 2. This is minus 1. 4. Sorry, no, this is 1 minus minus 2. So this becomes 3. So here we get 1 minus 2. This is 4. This is 3. 2 minus 2. Here, if we multiply with AB, this is equal to 0, 0. We need to find A and B. So 1 minus 2, we get, what is this? We get 3, 4. Here we get also 3, 4 times AB. This is equal to 0, 0. So can you find a pair of A and B's that satisfy this condition? This is 3A plus 4B is equal to 0. So what is a pair of AB?
Minus 4b over 3.
Minus 4B, let's do it.
4 over 3.
Minus 4, 3, this is the value. And then we have to look at the other eigenvalue. So let's write the other eigenvalue here. We say A minus lambda I, A minus 5 times I. This is equal to 1 minus 5 minus 4. This is 4. This is 3. And then we get 2 minus 5. We get minus 3. Are these two rows linearly dependent?
Yes, they are dependent.
Yes, they are. So what is a pair of A and B that satisfies this condition? We get minus 4A plus 4B. This is 0. So 1 and 1 is an option, right? So for matrix A, whenever lambda 1 is equal to minus 2, okay, the eigenvector, let's say B1, it was equal to minus 4, 3. Then, for the other eigenvalue, lambda 2 equal to 5, V2 was equal to 1, 1. Okay, so we found this is the matrix P. Now we need to find P inverse. What is P inverse? Now these equations, we have them on the board, so let's find it. Apparently, we found D, this is D, this is P, we need P inverse. What is P inverse? P inverse is 1 divided by the determinant of this matrix P. What is the determinant of matrix P?
Minus 7.
Minus 7. And then,
Then we exchange 1 with minus 4.
minus 1, minus 3. And this is going to be, you said 1 over, is it minus 7?
Yes.
Okay, then let's divide here by -7. Then we get the following. This will be 1/7 times -1, 1, 3, 4. That's good. We found the p-inverse, okay? So now we have the p-inverse, and now that we know the p-inverse, we can find u0. So the initial condition, so this is 1, 0, right? What is the initial condition here? So let's write this one when t is equal to 0. And this is when t is equal to 0. How can we move this way? We move it with p inverse, right? So then we say that we denoted those, actually, sorry, we wrote this bw. These are just random variables. Let's write this one bw. It's better if we write the bw because we might be confused with u, etc. So let's write it like this: v0 w0. This is equal to 1/7 times -1, 1, 3, 4 times what? Times this, right? Because we know that u0 as a vector should be equal to p inverse times x0. Because this is how we do the linear transformation from, actually we can draw it right here. So this is p inverse, and then we should be coming this way by the next p. Okay, so what is this? This is equal to 1/7 times what? -1, and then 3. So here we can say that V is equal to, what is V0? -1/7. -1/7 e to the power -2t, and this was equal to 3/7 times e to the power 5t. Okay, so so we found the V and W. Then we say that y1 as here's it here. y1 as a function of t and y2 as a function of t, they are equal to matrix P, which is -4, 3, 1, 1, times, what is ut? It is -1/7. -1/7 times e to the power -2t, e to the power -2t, and 3/7 e to the power 5t. This is the answer, okay? And the final answer is, let's multiply those. We get 4/7. This is 4/7 times e to the power -2t, plus 3/7 e to the power 5t. Then we have -3/7 times e to the power -2t, e to the power -2t, plus 3/7 times e to the power 5t. This is the final answer.
Use the power of the matrices here.
Say it again.
Can we use the matrix powers here?
No, we cannot.
Okay.
No, and you don't need it, actually, you don't need it. But this is the answer. So it looks like this differential equation that we have here, y1 and y2. How does y1 change as a function of time? y1, it is the linear combination of one exponentially decreasing function, which is e to the power -2t, plus some other exponential function, which is e to the power 5t. So if you are to draw these two functions, let's see what they are. So what is e to the power -2t? E to the power -2t is an exponentially decreasing function, which means that it is a function that is going to decrease like this. It's going to converge to 0. Okay? This is e to the power -2t. And then e to the power 5t, it is a very fast increasing exponential function. Okay? So this is time. This is time t, which means that y1 is equal to, so let's say, at any time t here is going to be 4/7 times this value, as they know this in red, plus 3/7 of this value. Okay? So we get 4/7 of this plus 3/7 of this. But y2, it is minus 3/7 of this plus 3/7 of this. So it looks like, yeah. This is the answer. A little later, at this time, again, we will have to add up respective values of these points, okay? So this would be relatively difficult to solve this differential equation when it is coupled, but what we did, we just did a change of variables. We went to a new domain, and we solved the problem as shown on the board. In fact, we really like to show everything a little more elegantly, so let's try to, we can even simplify this a little more. So we can say that y1, y2, this would be equal to, let's do here 1/7, so we can factor out 1/7, it's a constant. This is 4, 3, minus 3, 3, times e to the power minus 2t, e to the power minus 2t, and e to the power 5t. This is also an elegant way to write this, okay? Do you have any question?
Professor,
Yes.
when we put there 1/7 times minus 1/3,
Yes.
we got minus 1/3 by multiplying 1/0 there, didn't we?
Say it again.
Dacă te prove curzorom V0 W0, V0 ni premještat minus ni 3. Ato minus ni 3 shine, po, doli nga që shumëzojmë gjithë vektorët me një 0, apo ja? Okay.
Okay, so you get it here.
Okay.
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 Yeah. Any other question?
Any
Professor,
question?
I have a question.
Yes.
Continue, Albino, sorry.
Okay. To find lambdas, because we have done with other ways with Professor Drena, is always good to find it with, for example, lambda 1, lambda 2 equals to delta. Da thëmë me këtë, si që bë me këtë mënyrën, sepse me profesor Drena kemi rënë gjatë për gjetur lambdat.
No, they are both equivalent. So let's find it the other way around. So how do we find the lambdas? We do a minus lambda I, which is going to be 1 minus lambda 4, okay, 3, 2 minus lambda. We've done also together the long way, right? So we have done this before in our class also. So we try to write down the determinant of this one equal to 0, which is 1 minus lambda times 2 minus lambda minus 12, okay? Minus 12, this is equal to 0. Then here we get lambda squared, and then minus 3 lambda. Is this correct? Minus 3 lambda. I believe this is true. Then plus 2 minus 12. Plus 2 minus 12, this is minus 10. This is equal to 0. So this is the second order polynomial we are playing here.
Yeah. We're not second reflection to just go on. Okay.
Minus 5, 2, right? So this is lambda times minus 5 times lambda plus 2, okay? So this would be equivalent. Now, probably this is also short. It's not that much longer than the other one. Okay, they are comparable. Okay?
Po në rastin kur janë 3 lambda, si supozet bëhet ajo mënyra shkurt apo vetëm kështu gjatë?
Bëjmë një shembull që është matrizë 3 metra. Bëjmë atë shembull.
Okay.
Vëllë kishte pyetje?
Po, profesor. Këtu te VO dhe WO.
Po.
Kjo pjesa 1/7 minus 1, 3, 1, 4, kjo është P inverse.
Yes. It's here.
Po pse kemi shumëzuar me 1, 0 vector këtu? Tracing
Because it was
origin.
the initial condition. We said that initially we start with this.
Oh, okay, okay.
Okay. So yeah. Any other question? Okay, we can give a short break. We'll continue again.